All right, we want to be able to connect what we've been doing this week. We started off by defining what displacement was, how far you move from position to position. Then we said if we take the displacement and we figure out how much time it took, so that gives us the velocity. Then if we figure out how the velocity changes from one position to another and divide by the time it takes, we call that the acceleration. So we have these three things: displacement, velocity, and acceleration. And we've looked at them on motion diagrams. We've drawn arrows to represent them. And we've sprinkled in a little bit of graphing as well. All three of these things are connected through the graphs that we make. And so today we're kind of introing that. And then next week and in the lab that we'll do, we're going to actually make these graphs in order. Okay. So we'll start off with what we did so far this week, the order in which we went. So if we started with position and we figured out the change in position divided by the change in time, what math thing would we be doing to a graph of position versus time? Let's say this is what the graph looked like. What am I figuring out if I do the change in x divided by the change in time? Chad, what graph thing am I doing? All right, I'm figuring out the slope. Okay, so if I have a position graph and I calculate the slope, I would get velocity because it's the change in the position divided by the change in time. Okay, so now I would have some graph that was v versus t. Again, the graph might look, these are not the same graph. Well, actually, I'll do it like it's the same graph. This graph might look something like this, okay, where I graph the slope at every time. And if I figure out the change in velocity over the change in time, again, what graph operation am I doing? If I do the change in v now divided by the change in t, still figuring out the slope. Okay, so if I calculate the slope, what will that give me now? The acceleration. Okay, so this is just a recap of what we worked on. Each day we added a new piece. Tuesday we did position. Wednesday we did velocity. Yesterday we did acceleration. And every time we do this, we're figuring out the slope. Yeah. Time. Correct. And we could do this again. We could take, so if I figured out the slope for this velocity versus time graph, what would the slope of that line be? Gavin, what's the slope of this horizontal line here? Yeah, it is 0, right? There's no rise. So if I make the next graph of A versus T, these can be tough to draw, but it's at 0. Okay, and you could do this again. You could figure out the slope of the acceleration versus time graph. It's got a cool name. It's called the jerk. And this just keeps going, but we're stopping here. We're not going to keep finding the slope. What would the slope of this line be? Also 0, because it's 0 and it stays 0. Okay, so once we get to a slope of 0, we're not really interesting to keep going. Okay. Now, if we can use the slope to go in this direction, think of it like going kind of downhill from position to velocity to acceleration, we should be able to go the other way. I should be able to start with the acceleration, then figure out the velocity, and then figure out the position. Should be able to go in both directions. Think back to the 3 graph things we learned how to do at the beginning of this unit. What haven't we used yet? Or let's start with what have we done? What is one graph operation we've done to our graphs? Angela, what have we done to our graphs? It's on the board right now. Yeah. So we've calculated the slope. What else have we done to our graphs? Okay, so what is it that we haven't done? Okay, so we haven't necessarily read off positions, but we have looked at graphs and said, at this point, this is the value. So we've read off values and we've figured out the slope. What's the third thing we haven't done since you started looking at position? The third thing we haven't done. Look back in your notes. What's the third thing we haven't done yet? We introduced it, but we haven't done it since we started talking about position, velocity, and acceleration. Kirsten? Yeah, we haven't done the area yet. And that's what we're going to look at today. So this is where we're at. We said calculate the slope and you'll figure out these things. So if I go backwards and find the area, so let's say this is an acceleration versus time graph, and I find this area, that would tell me the change in velocity. And if I do it again, if I have a velocity versus time graph, and let's say that graph looks like this, and I figure out this area, that would tell me the change in position. It's kind of like if you took this graph and you said, or earlier, we said, for example, V equals the change in X over the change in time. Well, that's equivalent to V times the change in T equals delta X. All I did was cross multiply. So I turned finding a slope into finding an area. This is calculus at like the most basic level. Okay. Now we talked about the shapes we're going to do are just going to be rectangles and triangles. So we're going to do an example now, but we're not doing anything crazy. We're going to do, this would be the area of a rectangle. This would be the area of a triangle. And that's what we'll limit ourselves to. So something you'll need to know, and if you've started not the homework assignment due tonight, but the next one, it'll ask you things like, what is the slope of this graph represent? What does the area of this graph represent? Okay? So yeah, let's do an example. I'm going to start with an acceleration versus time graph. Yeah, let me give you one more minute on this slide. Yesterday's. Tuesdays.
Tomorrow.
Oh.
I mean, the one that's tonight.
Do tonight, yes.
I was doing it yesterday.
Okay.
But it was asking, because it was like an example.
Can you come by during a free period today to ask? Post it on the website and I'll respond. I can't do it right now. Okay, so let's look at an example, and we're going to start with this acceleration versus time graph. And we want to figure out the velocity versus time graph. Okay, so here's what we would do. I've got this chart, and I want to know what is the area between 0 and 1 seconds. And then I'll figure out the area between 0 and 2, and then 0 and 3, 0 and 4, 0 and 5. Okay. So let's do the 0 and 1. So I need to figure out this area. Okay. So what is the shape we have here? It's a rectangle. I just have to do base times height. How wide is the rectangle? 1 second. How tall is the rectangle? 1, and the units, meters per second squared. So what is that area? 1 meter per second. 1 meter per second, because this second cancels one of these. Okay, let's do the next area from 0 to 2 seconds. Okay. Now how wide is the rectangle? 2 seconds. How tall is the rectangle? Still 1 meter per second squared. And I multiply that, and now I get 2 meters per second squared. What would be the third one? And why is it 3? Which of those numbers is changing? The width or the height? The width, right? So this is 3 seconds, then 4 seconds, then 5 seconds. But the height, because it's a rectangle, stays the same. The square, we're reading it right off of the graph. Acceleration is measured in meters per second squared. You can see why, because when we multiply these two things, we should get velocity, and it should be meters per second. So we need one of the seconds to cancel out. So it becomes 1, 2, 3 meters per second, 4 meters per second, 5 meters per second. Think back to what we did yesterday. We were adding 1 meter per second every second that goes by. I think my next slide is just the numbers on here. Yeah, okay. So this is what we end up with when we find those 5 areas. And now what we can do is we can make a graph of velocity versus time. So to start, 0 seconds is going to be 0 meters per second. 1 will be 1 meter per second. 2 will be 2 meters per second. 3, 4, 5, and 5. I can turn this into ordered pairs. What do you expect that graph to look like? It's a straight line. Is it have positive slope or negative slope? Positive slope. And what is the slope? It's 1 meter per second squared. That's what we just, remember, this graph tells you this is the slope of the other graph. This graph tells you this is the slope of the velocity versus time graph. It says it's 1. It matches, right? We go increase 1 in 1 second. So they match. And this is what that graph would look like. Something like this. How do we know it started at 0? The question told us that. We're not going to focus too much on that today, but we will talk more about it next week. So these are my pairs: 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5. The slope is positive. It's +1, just like what the other graph told us. So we did it. We just did calculus together. That's really cool. Where we took the area of one graph, and it tells us about another graph. Okay, let's continue the process. Let's do this again. Okay, so now we're starting with the velocity versus time graph. And if we figure out the area under that, which graph should we get? Meryl, what graph should we get? Position versus time. So I can do the same thing. I can find these areas in the time intervals, and that will tell me this other graph. How is finding our areas different this time? Nicole, how is it different this time? So what, like, for example, let's say I wanted to do between 0 and 1. Right, I just have to figure out for this triangle. Before, it was a rectangle. So just to make sure I remember that, I'm going to write the 1/2 right away. Because the area of a triangle is 1/2 base times height. So I'm just going to write the half so I don't forget about it. 1/2. So from 0 to 1 seconds, what is the width of our triangle, or the base of our triangle? 1 in the unit, seconds. How tall is the rectangle? What is the height, of the triangle? 1 meter per second. So let's see, a half times 1 second times 1 meter per second. What does that give us? Shannon, what is that? A half times 1 times 1? Okay, so yeah, so the number is a half, and what happens to the units? The seconds cancel. A half meter. Awesome. Okay. Let's do the next one. What is now, for the next triangle, the half is there because we're talking about a triangle. Remember, the area of a triangle is 1/2 base times height. So now, let me do another triangle here. So this goes like this. What is the base of the blue triangle? 2, and the unit? Seconds. Now, what is the height of this triangle? 2 meters per second. So do a half times 2 times 2. That would be 2, and the unit is meters. Okay, try the third, fourth, and fifth one on your own. I'll give you 2 minutes. So I'll draw it to get you started for the third one. Okay, so the green one would be the third one. All right, and then so fill in the rest of the chart in your notes. And figure out 3, 4, and 5 seconds. Use this triangle to figure out 3, 4, and 5 seconds.
For number 3, we do the 1 times 3.
Times another 3.
So that becomes 1.5, and then we do the
4,
1.
and then 1.5 times 3, which should be 4.5. Again, you should have the next 3 distances. So what is it for 0 to 3, 0 to 4, and 0 to 5? Continue the pattern.
Is this correct?
0.5.
Yeah, there's a point there.
Oh, couldn't see it. Yeah, there you go. Okay, so for 0 to 3 seconds, Melody, what did you get? Okay, so what was the base of your triangle? And the height? Okay, so a half times 3 seconds times 3. Perfect. Awesome. Okay. All right, for 0 to 4 seconds, what do we get for Caitlin? 0 to 4 seconds. So 4 seconds times 4 meters per second, which is 8 meters. And then 0 to 5, Angela. Okay, so 5 seconds times 5 meters per second, 12.5 meters. Okay. So my next slide just has that. The numbers, okay? So 0.5, 2, 4.58, and then 12.5. What do you expect this graph to look like? Well, so it's definitely increasing, right? Every second that goes by, we're farther away. It's not a constant change. It's going to have a curve to it. It ends up looking like a parabola. Okay, next week we'll be able to say exactly why it has this shape. Well, this is what we saw on yesterday when we did the acceleration piece. Okay, so what is the connection here? At every point, if I said, for example, what is the slope at 4 seconds? Okay, and I draw this line here. If I go back to the velocity graph, it will tell me, oh, at 4 seconds, that slope there was 4 meters per second. And if I want to know what was the slope at 2 seconds, I don't have to calculate it. I could look back at the previous graph. At 2 seconds, it told us it was 2 meters per second. The other thing, and some people have been asking about this, about the concavity. What is the concavity of this graph? Positive or negative? Positive. In fact, it is positive 1. So what is the connection between the concavity and the graphs that we've made? Where have we seen? I'll go one step further. The concavity is 1 meter per second squared. So where is the concavity connected to all of this? It's a cool one. Here, go one more. So slope would be velocity. We need to do the slope again, acceleration. So this, the concavity of this graph is equal to what the acceleration was. That's like a next level thing. But that's the connection. If our acceleration was negative 1 meter per second squared, this graph would curve and have negative. And we'll see examples of that next week. But that's sort of the connection between all of these different things, between the position, velocity, acceleration, and whether you're doing slope or area, you can get one or the other. Kirsten? Yes. Yep. Shall I? No. So this stuff starts, it's due a week from today. And we're going to do practice with this next week. So the one due tonight is just the velocity. And then the one Tuesday is acceleration. And then the next one is this graphing stuff. Good question. What are we thinking? This is really cool. Like this is what Isaac Newton, this was his major contribution, was saying you can connect all of these graphs in the way that we just did. And obviously it's a really big deal because if you think about it, all we can measure is where things are located. There's no real way to say, oh, well, how fast is it going? You can't really do that with a meter stick and a ruler unless you collect a lot of data. And that's sort of the connection between these things here. And what we're going to do as a lab activity is you're going to make one of those motion diagrams that moves using Google Slides. And then you're going to animate what the graphs look like. I'm like really excited. It's a really fun thing that we're going to be doing. So that's sort of the connection between all this stuff. All right, so I did have another example for you to work on, but we'll save that one for another day. Yes.
Are we gonna
No. So you're going to use the same website I did to make it animated, and then maybe we'll like throw them up so people can see the different animations, but you won't have to talk about it.